Hello boys and girls, this is Daniel for Rock the JVM, and in this video I'm going to show you a famous interview algorithmic style question called N queens. Now, why is this video different? The video is different because I'm going to show you a direct preview at one of the videos and one of the lessons of the Scala and Functional Programming Interview Practice course, in which I deconstruct various interview style questions and I solve them with Scala and pure functional programming. And I'm going to leave links in the description to this video. So this will assume that you're comfortable writing Scala, and I will recommend that you wait and try to program this problem yourself. I'm going to give you a recommended waiting time in which you're going to try your hand at this problem and then write alongside me and try to solve this problem yourself so that you take away the maximum amount possible. This video and this course is applicable to both Scala 2 and Scala 3 because the concepts have not changed. So I hope you'll like this video, and I hope you will like the course if you choose to enroll in it. This will make you a great functional programmer. That being said, let's introduce the N queens problem. So this is a classical problem in computer science which sounds something like this. Given the dimensions of a square chessboard n, we want to find the positions of n queens on the board in safe position. That means that they are unable to attack each other. Now, from the basic rules of chess, two queens can attack if they are on the same row, on the same column, or if there is a diagonal path between them. So that being said, let's get back to our project and let's continue with this problem in the code. So I'm going to create a new Scala application for this problem. I'm going to call this n queens. Make it an object, extends app. Let me collapse the menu and let's define the n queens problem, which takes n as an int and will return a list of int, where every list of int is a possible solution to the n queens problem, and we want to return all the possible solutions to the n queens problem. All right, so I think you got the picture of what the problem wants. I will give you between 30 minutes to an hour to solve this problem. Obviously, I will recommend tail recursion. The stack recursive version for this problem is frankly even more difficult than the tail recursive version. If I'm wrong, please correct me in the Slack room, but do work with tail recursion in this problem. So pause the video now and I will come back with a solution right after that. All right, so when you're ready, let's get started. So obviously I will implement this in a tail recursive fashion, but I will need two auxiliary functions. So I will define an auxiliary function that I'm going to call conflict, and I'm going to pass two arguments to this. The first is the position that I'm trying to place the queen in. So position will be an int, and the queens will be a list of int. And this will return a boolean. And this conflict will return true if the position is under attack or can be under attack by either of these queens from this list. And the other function that I'm going to write will be a backtracking tail recursive algorithm that I'm going to call n queens tailrec. And I'm going to try a position that I'm going to call current position as an int. I'm also going to keep track of the current queens that I've placed on the board as a list of int, and the solutions as a list int, which will aggregate my entire result. And this function will return the list int that I want. All right, now let's go to the conflict and let's fix that first. So conflict will return true if this position can be under attack by either of these queens. So I will define an auxiliary function. Let's call this conflict one queen, which will take the position as an int, a queen as an int, and the index at which this queen is at as an int. And this will return a boolean. And this position can be under attack by this queen if queen equals position, that is, they're both on the same column. So the queen is the column position on the board at the given row. So this index is the row at which the queen is in. Or index plus 1 is equal to position minus queen. So this is one diagonal. Or index plus 1 is equal to queen minus position. So this is the other diagonal. So this position is in conflict with a queen, that is, can be attacked by this queen. If this position is equal to the queen, that is, they're all in the same column, or they're on one diagonal, or they're on the other diagonal. All right. Now I'm going to call this conflict one queen function for all the queens in this list. So I'm going to call queens.zip with index, which will return a list containing the value itself, which is the column value of the queen, plus the index, which is the row of the queen. And I'm going to do a filter. So I will do a pair arrow. Actually, let me expand that with a proper block. So pair, I will do val queen and index to be the pair. And the predicate should be that conflict one queen with position queen and index should return true. So this expression will give me back the list of queens that can attack this position. Now we have a conflict if this list is not empty. So is empty, and then we put a not at the beginning. Now the IDE is smart enough to suggest that the filter plus not empty means exists. So I'm going to do exists, and I'm going to kill is empty, and I'm going to also remove the not check. So we are in conflict if there is at least one queen that can attack this position. Good. Now, this backtracking algorithm is not terrible to write, and we need to be very careful of how we chain our conditions. So when do we stop? We will stop when the current position is bigger than n, or bigger than or equal to n, and the current queen is empty, meaning that I'm out of options. So I will do if current position is bigger than or equal to n, and the current queens is empty, then I've tried all the possible combinations of queens on the board. So I will return the solutions that I have. Otherwise, if current position is bigger than or equal to n, then it means that the current queens is not empty, which means that I'm out of options for this particular row. So I need to backtrack. So I will do n queens tail rec, and the current position will be the current queen's head plus 1, so I will go back one row, and the previous queen I will move by one position. So I will do current queen's dot head plus 1, and then I will do current queen's tail, and the same solutions. Now, this particular recursive call is very hard to visualize. So if you're not visualizing your own solution on this one, I will ask that you be a little patient so that I can show you with an actual use case. All right. Otherwise, if I'm in conflict between the current position and the current queens, so here's where we will use the conflict auxiliary function. So if conflict between the current position and the current queens, then it means that this current position is not valid, given the positions of the current queens that I have on the board. And so I will try the next position. So I will recursively call n queens tail rec with current position plus 1, the same current queens, and the same solutions. Now this code is pretty compact. Let me put some curly braces here so that we can visualize the recursive call more easily. Otherwise, at this point, current solution is valid in the context of the current queens. And so if the current queens are exactly n-1, so if I have n-1 queens, then I'm just placing my last queen on the board. And so I'm just building up a solution. So if the current queens dot length is equal to n-1, then I just have a solution. Then let me build a solution. So val new solution as current position : current queens. All right. And then I will need to simply call n queens tail rec with current position plus 1. So I'm still able to try the next position, the same current queens, and new solution : solutions. So I'm adding the solution to the list of solutions that I've accumulated. Otherwise, the queen is still valid in the context of the current queens, but the solution is partial. So I will call n queens tail rec with 0 because I'm starting on a new row. The current queens will contain the current position, so I'm going to do current position colon colon current queens and the same list of solutions. And this is the tail recursive backtracking algorithm. And finally, we will call n queens tail rec. Current position will start at 0, current queens will start as the empty list, and the solutions accumulator will start as the empty list. Now, n queens tail rec is obviously tail recursive, and let's work through a use case just to visualize how this code will work. And I will do n queens with 4 because 4 is the smallest number for which we do have solutions. So that will be n queens tail rec with 0, the empty list, and empty list. This will take a bit of time. So let me start with an empty chessboard, which looks something like this, that I've drawn in my notepad, just for you to visualize how the code will actually work. So the list of current queens will be visualized something like this. All right, so I'm going to start with current position 0. Current position is not bigger than 4. I'm not in conflict, nor am I at the end, and so I will be here on the last branch. And so this will be n queens tail rec with same 0, current position colon colon current queens, which is the list containing 0, and the solutions, which is the empty list. And so I've attempted at placing my first queen here, where I've put the X. And now I'm calling NQT with the current position 0, and so I'm attempting at placing the queen here where the highlighted bit is here on the screen. And so I am in conflict because the conflict will tell if this position is under attack by this queen, being on the same column it is, and so I will try the next position. So this will be NQT with 1, the same list 0, and the same empty list for solutions. And so I will attempt at placing my queen here on current position 1. I'm still in conflict because I'm on a diagonal, and so I will try the next position. So NQT with 2, the list 0, and the list empty. So I'm attempting at placing my queen here. Now, I'm not in conflict, and so I will be here on the final branch as well. So I will do NQT with current position 0 and the current queens 2, 0, and the empty list. So I've just placed my queen here on position 2 on row number 1. Now, I'm calling NQT with current position 0, which I'm attempting at placing the queen right over here where the blue square is. Now, because it's under conflict by the first queen, I will skip that, and so I will call nqueens tail rec with 1, the same list 2, 0, and the empty list. 1 is also in conflict, so I'm going to try the next one, NQT with 2, the same list 2, 0, and the empty list. 2 is under conflict again by the queen above it, so I'm going to call NQT with 3 and the same list 2, 0, and the empty list. So I'm going to attempt to place my queen here, but it's again under conflict by the queen above because it's on a diagonal, and so I'm at n queens tail rec with 4 and 2, 0, and empty list. And 4 is outside of the range of the chessboard, and I'm right over here under the second branch. The current position is bigger than n, but the current queens is not empty, and so I will need to backtrack. And here's how the recursive call will start to make sense now, because the next position that I will try is going to be to move the previously arranged queen. So I'm going to try to move this particular queen one step ahead. So I will do current queens.head, which is 2, and I will attempt to move it by 1 position. So I'm going to attempt to take this out, and I'm going to attempt to move it over here where the blue square is. And so this will be NQT with 3 and the list 0 and the empty list. So because that's what the recursive call says. We're doing current queen's head plus 1, so that's 2 plus 1, 3. Current queen's tail, which is the list containing just 0, and the empty list. So I'm attempting at placing my second queen here on the last row. Now, this queen that I'm trying to place is not under conflict with any of the previous queens, and so I'm okay with placing it here and calling NQT recursively with index 0, the list 3, 0, and the empty list. Now, 0 means I'm attempting at placing the third queen over here at column 0, which is under conflict. So I'm going to call NQT with 1, 3, 0, and the empty list. 1 is not under conflict with any of the queens, so I'm going to place it here, and I'm going to call NQT with index 0 and the list 1, 3, 0, and the empty list. Now, you will find that all of these positions are under conflict. So I'm going to try in turn NQT with 1 and 1, 3, 0, which is under conflict, 2 with 1, 3, 0, which is under conflict, and 3 with 1, 3, 0, which is under conflict. And then I'm going to call NQT with 4 and 1, 3, 0, which is, again, with my backtracking branch. And so I will pop the first queen out of my list, and I will call NQT with 1 plus 1, which is 2, and the list 3, 0, and the empty list. So I'm going to take my queen out of the position, and I'm going to attempt it at placing here. Now, the indices 2 and 3 are under conflict with the second queen, and so this will be NQT with 3 and 3, 0, and 4 with 3, 0. Now, again, I will be under my second branch yet again, and so I will take my second queen and pop it out of the list. So that will be NQT with 3 plus 1, which is 4, the list containing just the element 0, which is my first queen, and the empty list. So I've just popped my second queen out of the chessboard. Now, because I'm out of the chessboard yet again, I will need to pop my first queen out of the chessboard and try again. So that's NQT with 1, the empty list, and empty list. So I've just moved this queen from here to here. Now, notice the number of steps. So we've taken quite a lot of steps just to arrive at this stage, and we haven't even found a solution. So I trust that you follow the algorithm now. You understand how the code works. This algorithm is a backtracking one, which means it tries all the possible solutions. If I carry on at this pace, and I think I'm talking pretty fast, it'll take me a good couple of hours to work through this use case alone. So I trust that you know how the algorithm works. Now, we will simply try all the possible solutions. Now, that being said, let's just print out, so print line, n queens with 4, because with this particular arrangement, there are two possible solutions. There is, let me copy this one, there is this one where I put the queens over here. So we need the list 1, 3, 0, 2. And there's also a very symmetrical solution. Let me change the formatting here, where the queens are like this. So let me change this. So the queen is here, this queen is over here, and the last queen is on second position. So we will need the list 1, 3, 0, 2. And the list 2, 0, 3, 1. Right? So these are the two solutions for n equals 4. There are no other solutions for n equals 4. So let's go check these out. Let's run this application, and hopefully we get this list. So we have 1, 3, 0, 2 and 2, 0, 3, 1. All right, so let's break down this algorithm one last time. So this is, the first condition is when I'm out of options. So I'll return the solutions that I have. The second branch will be I'm out of options on this particular row. So I'm out of options on this row. So I will need to move the previous queen by 1. Okay, so this is what the recursion is going to do. Now, let me move this comment inside. Okay, now, if I'm in conflict, then I will be free to try next position. So conflict with the other queens, try next position. Now, else if current queen's length is n-1, I've just built a solution. Otherwise, this particular branch, this last one, means that the current position is valid in the context of current queens. So I'm free to try the next queen. So try next queen on the next row, as this one is valid. Okay, so I hope that makes sense. Now, if you want to be really aesthetic and you want to also see the solutions yourself so that these lists are not really visually appealing, let's also make them pretty printable. So I'm going to define a function called prettyprint, which takes a solution as a list of int and will return a string. So I'm going to define an auxiliary function inside the n-queens problem that takes a solution as a list of int and will return a string that will look something like what I've drawn here in the use case explanation. Now, I'm going to make the n-queens problem return a list of string. And at the very end, when I call n-queens tailrec, I'm going to map each solution to the prettyprint function. So let me start by creating the top edge of the board. So I'm going to do 1 to n dot map, and I'm going to put an underscore. So if I have a board of size n, I will need n underscores, and I will need some dots in between. So I'm going to do make string with dot at the beginning, dot in between each element, and another dot at the very end. So this will be the string dot underscore dot underscore dot underscore dot underscore dot. Okay. Now I will need to compute the rows. So I will need solution dot map, and for every queen, I will do the following. I will need to compute whatever is before the queen and whatever is after the queen. So I will need the n cells to the left. So I will create val cells before as 1 until queen. So this is very important. 1 until queen dot map, and for every element I'm going to put in an underscore. Now I'm going to create the before string as if the cells before is empty, then I will need to return just a plain bar. For example, for the queen equals 0 here, I will simply need to return a plain bar. Otherwise, I will do cells before dot make string, and I'm going to put a bar in between each string. But not only that, but I will need to also put a bar before and after the bars here. So the cells before will look something like this, and I need to put a bar before and after this string. Okay, and I will have to do the same with the after cells. So I'm going to do cells after as queen plus 1 until n dot map, and again I will put in some underscores, and I'm going to do the same thing. Now let me put queen plus 1 in parentheses so that the compiler is not confused, and I'm going to write an after string in much the same way. So if cells after is empty, then I'm going to simply return the bar string, else cells after dot make string, and I'm going to put 3 bars, before, in between, and after. Cool. Now all I need to do is compose the before string, the x, and the after string. So this will be before string plus a small x plus the after string. Okay. Now these are the rows. Now I need to concatenate the top edge, and I need to compose these rows with a \n in between them. So I'm going to write an s-interpolated string in which I'm going to put the top edge, and then I'm going to do a \n, and then I'm going to evaluate rows.makeString with a \n in between each row. Okay, so I hope this works. Let me run this and see how this works. All right, so we have the list printed fine. Let's do nqueens.for dot for each print line so that we can see each string in action. Okay, I have an extra of one cell that doesn't work properly, which is the cell before the queen. So I'll need to do 1 until queen. Yeah, that's 0 until queen because the indices start at 0. So if I run this again, these are my solutions. All right, this was tough. Let's solve the n queens for a bigger number. Let's call this val q8 as the famous 8 queen problem. So n queens with chessboard of dimension 8. And then let's call this printable solution as q8 dot make string, and then I'm going to put 2 backslash n's in between each solution. And then I'm going to print line the printable solution. And then I'm also going to print the number of solutions for 8 queens. So I'm going to say print line, and I'm going to put an s-interpolated string, total solutions, and then I'm going to inject q8 dot length. All right, so for q8, if I remember correctly, we should have 92 solutions. So let's go ahead and run this and wrap this problem. So notice we have 92 solutions, so I was correct, and each solution is now verifiable visually. So as you can tell, there are new 2 queens that can attack each other. All right, this was hard. So if you did this problem yourself, congratulations, this was pretty tough. I'll be waiting for you in the next video.